So we are starting the class. So you can hear me, right? So in this week we will be discussing the Scott connection. So I am audible, okay. So in this class we have some Scott connection, open delta connection. These connections I was unable to discuss in the last class, right? I wrote it that I'll discuss, but I'll discuss it in today's class. So today we'll be discussing the Scott connection. ठीक है? Open delta connection, also called as V connection. Then we will discuss the parallel operation of the transformers. Okay. And then we will see the last year's assignment questions. So you will find that this week's assignment questions are also similar. Okay. So here let us start with our discussion. So first we will be starting with the Scott connection. Okay. So Scott connection or three-phase to two-phase connection. So, as I have discussed in the last class also, that the n-phase system, so we have an n-phase system, okay? Suppose three-phase system, two-phase system, like that n-phase system is made up of n single-phase systems. Okay. Displaced by 2 pi by 9 degrees. Okay. This is valid for n greater than 3. Okay. N greater than or equal to 3. So suppose you have a three-phase system. So what is the angle displacement between them? It is 360 degree by 3, which is 120 degrees. Okay, like that. But for two-phase system, this formula is not valid. Okay. So for a two-phase system, there is a phase shift of 90 degree. Okay. So 90 degree is the phase shift. Okay. So here in all my derivations, I am taking like this. So you will be seeing in the Scott connection that from a three-phase connection, we will be getting a two-phase connection. Now in that two-phase connection, on the you will see on the I will be having two phases like this. So I am taking that the VA phase is leading the VB phase by 90 degree. Okay. So here I am taking that the leading phase is A. And generally this Scott connection, like this, what you say, this your two-phase systems are generally used secondary voltage for arc furnace. Okay, so this is generally used for arc furnace. Okay. So you will see that with the questions also, they will be saying that the Scott connection on the three-phase side, you're giving the supply, and on the two-phase side, you have a arc furnace. Okay, so this is the application of a two-phase system. So let us start with the Scott connection. So here it is made up of two transformers. Okay, so it is made up of two transformers. namely main transformer and teaser transformer. So you see, if we have to do a three-phase to two-phase conversion, so let us see the kind of what you say this phase diagram we will get. So let me draw the phasor diagram. So here, let us suppose that we have a three-phase system like this. So let us say this is the three-phase. 1 second. So here we are looking at the Scott connection. So Scott connection does three-phase to two-phase conversion. So I am drawing the phasor diagram, okay, for the Scott connection. So here you have this and you have this. So this is suppose A phase, this is B phasor, this is C phasor, okay. And here, if you see, this is like this, okay. You understand this is like this, A, B, C. I have just rearranged them to form a triangle, okay. Nothing different here, okay. Now here, if you see, if I take a perpendicular from A to this BC, this is perpendicular. So let us call this point M. So you can see that this point AM is perpendicular to BC. Okay. So this is the this is the kind of connection. If we do a connection such that if we take a what you say voltage point, if we take the voltage point between the midpoint of the BC and this point A, then that AM will be perpendicular to BC. Okay. So this is the idea behind the Scott connection. So if you will see, if we are giving the supply V1 to AB, V1 to AC, V1 to BC, basically three-phase balance supply. Now, three-phase balance supply means the magnitudes three-phase balance supply to A, B, C, with magnitude V1. Okay, so let me write it. With magnitude V1, and this what you say, this phase lag as in a three-phase system is 120 degree. Okay, so B phase is lagging A phase by 120 degree. C phase is leading the A phase by 120 degree, like that. Okay, so this is a three-phase balance supply. So if we do that, if we give a three-phase balance supply, but if we tap a point at the midpoint of this BC phase and we take this AM line, so you will see that this AM will be perpendicular to BC, which is the 90 degree. But you know that in an equilateral triangle, this basically this line this what you say, this magnitude is root 3 by 2 V1. So you can see that its magnitude will be root 3 by 2 V1, but it is perpendicular to BC. Okay, so let us make a connection like this so that we can get this kind of phase sequence. Okay, so how it will be, so let me draw that. So here this is A, this is C, this is B. So basically, this is the primary winding of the one transformer, and this is the primary winding of the second transformer. Now, how about the secondary winding of the transformers? So this transformer is called as your teaser transformer. So let me first draw the circuit, then you will understand. Okay. So let me draw the secondary side with another color so that it will be clear. So this side I am representing it as capital VA. Okay. So this I am writing it as capital VA. And on this side, there is another transformer. This I am writing it as VB. Okay, so here also some load is connected. So this is the point here. This is the point here. This is the point here. And this is the point here. Okay, like this. So you see, as I have drawn earlier, the phase sequence which we are expecting, which is this VA leading 90° by VB. So you will see that I will derive, and you will see that this phase sequence VA will be leading the phase sequence VB by 90°. Okay. So let us see how that is happening. Then let me write down what each of these transformers are called. So this is called as teaser transformer, and this is main transformer. So this, because this is taken at the midpoint, so let us say this is N1 by 2, N1 by 2. So this total turns of this main transformer is N1 here, and total turns on the secondary side of this main transformer is N2. Okay. Now here also on the secondary side, we are having the number of turns as N2, but you remember that, see, if we want to get a two-phase voltage from a three-phase voltage, so what we are expecting? We are expecting that these two voltages VA and VB are same in magnitude, and VA is leading VB by 90°, right? We want a phase difference between the 90°, and these two should be what you say same in magnitude, so they are a balanced two-phase supply. Okay. Now here, if you remember, this is N2. Now here we will take this number of turns on the primary of the teaser winding as √3 by 2 N1. You will understand why we are taking that, like from the mathematics you will understand. Okay. Now let me mark the current directions also, the currents which is flowing through these transformers. So let us mark with this. So here, this is IA, this is IC, this is IBC. Now you see this IA is coming downwards, IA, and then it gets divided into these two parts because these number of turns are same. So it is seeing the, like if it is seeing the same impedance, so this current will divide like IA by 2 here and IA by 2 here. Okay. And the current, let us take this is as IBC. Okay. So current here, this is IBC. So this IBC is flowing like this. Okay. So just I have marked this current so that it is easy to understand. Okay. So let me go to the next slide. Okay. So let me take this picture because then it will be easier to relate. Okay. New on the next slide so that we can derive the things. Okay. So now let us derive some of the things. Okay. So here now we will be deriving the number of turns, which is why this I took as root 3 by 2 n1, not n1. Okay, so let us see now. So first of all, this is the main transformer. Now main transformer is this one, right? So in the main transformer, the voltage ratio, this trans ratio is n1 is to n2. Okay, and remember this AC, A phase, B phase, C phase, we are all supplying V1. Okay, so you see this AC, basically you see V1 is what? V1 is AB, AC, BC. Okay, so this AC, BC, AC like this, all are V1. So here we are supplying V1. Here we are supplying V1. Okay. And you will see between A and B also it will be V1. Okay. So that is what we are giving a three-phase balanced voltage supply. Now this is the turns ratio. Now what about the teaser transformer? So teaser transformer turns ratio we have taken like this. So you see on this side, across the teaser transformer, we are supplying so you see across this main transformer we are supplying V1, which is clearly visible, right? Because C and B are the terminals of the main transformer. We are supplying V1. But if we supply V1 across this AC terminals, we know from this equilateral triangle that this perpendicular will have root 3 by 2 V1 across it. So what will happen across this primary winding of the transformer, we will have root 3 by 2 V1. Okay. So if V1 is supplied between AB, BC, AC. Okay, if V1 is supplied like this, so let me write this point. So let us write this as M. Okay. So across AM, primary winding of teaser transformer, we will have root 3 by 2 V1. Okay. And across BC or primary winding of main transformer, we have V1. So what will happen due to this ratio, if you see this ratio, right? So what is this ratio? AM N1 is to N2, or you see this suppose let us call it as VT1, VT2. So this will be equal to VT1 by VT2. T1 means teaser, teaser primary, teaser secondary. And let us call this as main VM1. And this, let us call the secondary as VM2. Okay. And this will be equal to VM1 by VM2. Now, you see VM1 be across BC, which is the primary winding of the main transformer, we are giving V1. So we can find what will be VM2. Similarly, here across the primary winding of the teaser transformer, we are getting root 3 by 2 V1. If we give V1 at AC, so we get root 3 by 2 V1. Okay. So this is root 3 by 2 V1 by VT2. So if you cross multiply, you will see that across the VA or VM2 or VT2, you get V1 by AM. And similarly, across what if you see this, if across this VB or VM2, you get V1 by AM. So in this way, because we took this root 3 by 2 N1 turns on this, what you say, this teaser primary transformer winding. So because of this voltages on the secondary side comes out to be equal. Okay, and we know that these are 90-degree, because if we draw the phasor diagram for these, this is the phasor diagram for the Scott connection. So this is the phasor diagram. Okay, so from the phasor diagram we can see that the voltage VAM is 90-degree to voltage VBC. Now in phase with VAM we have the secondary winding, so capital VA will also be in phase with this, what you say, this perpendicular branch, and on this VBC is in phase with the main transformer, so this VB will become the, what you say, base of this triangle. Okay, so like this we can get the 90-degree, and also the voltage magnitudes are balanced. Now let us see the currents. Okay, so let us find out what about the currents. If the secondary side currents, if we say that the secondary side current, suppose here is IB, okay, and this current is IA. So what about this current IA, capital IC, capital IB? Okay, what about these currents? So let me write here as capital IB also. Okay, so let us now write down. Okay, so from that you will see that this IB, first of all, if you see this IA, okay, IA is here and small ia is here. Okay, so what is the ratio between IA and small ia? So it is like this, that we can get from the turns ratio, right? So let us write it. So it will become like this, that IA by small ia is 1 by 80. So this becomes what? So your this becomes, so capital IA becomes IA by root 3 AM by 2. Okay, so this is the magnitude wise we get. Okay, so here if you see, this is the relation between small ia and capital IA in terms of the, what you say, turns ratio, root 3 by 2, N1 is to N2. We know that the current turns ratio is inverse, like if this, if VT1 by VT2 is 80, then capital IA by small ia will become 1 by 80. So that is only what I have written, and then I have derived the magnitude of capital IA in terms of small ia. Okay, that is it. Now let us write the current IB and IC magnitudes. Okay, so let me write it. So here IB, if you see IB, so this is the IB current. Now what about the IB current? IB current is nothing but this IBC minus IA2, because IA2 is coming down like this and IBC is going like this. So IB, which is effective IB, because you see when the current IB will flow here, so what will happen is that IBC will also start to flow. Okay, because it is what you say, this current in this transformer is leaving the dot, so IBC starts to flow entering the dot. Okay, as for the transformer, so IBC is flowing like this, and IA2, you see IA2, IA is leaving the small IA in the load on the secondary side of the teaser transformer is leaving the dot. So IA is current flows in what you say, entering the dot for the MMF balance. Okay, so for the transformer action, the current should enter the dot here. So IA flows like this. So on the basis of this IA and IBC, which flows due to this small ia and small ib, due to on the secondary side, due to the loads connected across them, we have to now find what are the values of IB and IC. Okay, so this IB and IC we have to find from this IA IBC. So we know that this IA is anyway same as the A phase current, so we don't have to solve for it again. But this IB and IC, we have to express them in terms of IBC and IA. Okay, so you see here, so this is IA, so this is IA, this is IA. Okay, so you see, because IBC is flowing like this and I capital A by 2 is flowing like this, so IB using the KCL comes out to be like this. Okay, so IB is IBC minus IA by 2. And what about IC? So IC is like this, but both IBC and IA by 2 are flowing like this. So see, IBC will be flowing like this. IBC will be flowing like this. And IA by 2 is flowing like this. So IC is what? IC becomes minus IBC by 2. So IC becomes minus of IBC plus IA by 2. Okay. So let us draw the phasor diagram. Okay, so let us draw the phasor diagram for the currents. So for now, so we know that the voltage phasors are like this, that VA is here and VB is here. Okay, so this VA is here, VB is here. Now, if for a unity power factor load, for unity power factor load, your IA and IB will also be in this direction. So IA and IB will also be in this direction. So this will be your IA, okay, and this will be your IB, okay, in phase with the voltages. So now let me draw the phasor diagram for the currents. Now you see what happens. So here IA, because it is in phase with the VA, it is leading the IBC by 90 degree. IB or IBC. Okay? And here IA, capital IA. So capital IA in terms of small ia is what? 2 by root 3 AM. Okay. So you see the primary currents and secondary currents will be in phase, but the only difference will be in their turns ratio. Okay. Now what about this? IBC is small IB by AM. Okay. So this is the primary side current. So if the secondary currents are flowing like this, that this IA is in phase with VA and this IB is in phase with VB. So this capital IA will be also in phase with IA. So capital IA is in phase with small IA, but having some what is a turns ratio. And what you say, this IBC, which is flowing on the primary side of the main transformer, is in phase with the small IB with this turns ratio. Okay, so that is how I'm drawing. Now here, this is minus IBC. Okay, so you see this IBC minus IA by 2. So this is IA, so minus IA by 2 will be here. So this is minus IA by 2. So IBC minus IA by 2 is what? IB. Okay, so IB is like this. So this is IB. Okay, and minus IBC by 2 minus IA by 2, this is IC. So you see, this is 90 degree, but if we can prove that this is 30 degree, this is 30 degree, then we can prove that, okay, this is a balanced three-phase current. So these currents IA, IB, IC, which are flowing in the primary due to the secondary currents, are balanced, because 90 plus 30, 120 degree, and then again 90 plus 30, 120 degree lead. So like this, we get the three-phase balanced current. Okay. So you see, this, so you see, we know that this minus IA by 2, so this becomes what? This becomes small IA by root 3 AM, like this. So this capital IA by 2 I can write like this also. This 2 factor will go, so this will be the current remaining. Okay, and so this is the current. Now what about this? This is IB by AM. Now you see the tan 30. Okay, and remember, this IA and IB magnitudes for the balanced load is same. Okay, so magnitude of IA is same as magnitude of IB. So if I take tan 30, you will see that this, what you say, this what you say, this perpendicular by base, it will come out to be like this. Okay, so it will be so let us say that this is I2. So you will see that this will come out to be, you see just the magnitude of it, into AM by I2. So this is 1 by root 3. So in this way, we can prove that this is 30 degree. Okay, like this for this triangle also, you can prove that if you do this perpendicular by base, this comes out to be 30 degree. Okay, so in this way, you can see that this is the three-phase balanced currents. Okay, so till now, is there any doubt here? Okay, so if there is any doubt, you ask. Okay, and as anytime you have the doubt regarding how the things are happening, you ask me. Okay, so this is how the Scott connection is. So in this way, what we got from a three-phased balance, if we give a three-phased balance supply to this Scott connected system, then we get a two-phased balanced voltages. Okay, and we have seen that if in this two-phased if we give a two-phased balanced load to this, and the currents which flows in this load side, then you will see that the currents which we obtain on the primary are also three-phase balanced currents. Okay, due to this Scott connection. So you can see that this is a three-phase to two-phase conversion. Now we will see what you say, the V connection or open delta connection. Okay, so let us see that quickly. So here we will see open delta or V connection. So here it is like this, that if suppose you have the, what you say, closed delta, like normal your delta delta connection. So how the normal delta delta connected transformers look like, we have seen in the previous class. Okay, so this is A2. We have seen the what you say, vector groups also, right? Now here I am drawing the normal delta delta connection. Okay, and then we will see how to make the, what you say, this open delta connection using this. This is A2, this is B2, C2. We have A1, B1, C1. This is like this is like this, and this is like this. Okay. Now, let us see what happens if I connect a three-phase load at the output of the secondary windings. Okay, so if this is the current I, then let me first finish this. So here we have seen from the previous class that if this is the current I, okay, then this current comes out to be root 3I. For the delta connection, the line current is root 3 times the phase current. Okay, and it is leading also by 30 degree. Now here, these are the currents. Now let us see, this is the voltage. Okay, so let us say this is the voltage V. Now what will be the power? S delta delta, it will be root 3 V line to line IL. So if you see, this is root 3, line to line voltage is V. Line to line voltage and phase voltage is same for the delta, so it is the same. So this is V, and line current we have seen, it is root 3I. So this comes out to be 3VI. Now let us see what happens in the open delta connection. Okay. So in the open delta connection, how it comes out, let us draw. So here what we do, we remove one winding. Okay. So let us see how it looks like. So here it is like this. This is C2. A1, C1. Okay. Here also in the similar way, we can draw it. This is A1. This is A2. This is A2. This is C2, C1. Okay. Now here also we will connect the three-phase load, and I'll show you what is the kind of voltage and currents which we get. Okay. So here the current flowing here is IA. The current flowing here is IB. The current flowing here is IC. Okay. So this is the situation. Now you see, so now let me derive the, what you say, this power expressions using the phasor diagrams. Okay. So let me derive it. So again, let us take that there. Okay. Okay. So let us write down how we can calculate the power. So first of all, you see this is IA, IB, IC. Okay. Now you see IB is like this. So IB is also flowing out like here like this. Okay. Now IC is here like in this direction. Okay. Now, so first of all, you will see that if we apply the voltage V here, okay. So this power in open delta is written like this, is root 3 VI. Okay, in the previous case it was 3 VI, but here you will see that root 3 into V line to line, which is V, and I line to line current is same as their phase current. Okay, you will see that it will, you see this IB is same as this IB, IC is same here like that. Okay, so you will see that it will come out to be same as the phase current. Okay, so this SVLL by S delta delta, okay, this comes out to be root 3 VI by 3 VI. So if we remove one winding, so the power comes down by 1 by root 3 times, which is about 57.7%. Okay. So you see, if we remove the one winding, we save some cost in that, but there is a power reduction in this much. Okay. Now let us see how to basically draw the phasor diagram. So here we have VAN, we have VBN, and then we have VCN. Now you see the power. First of all, let us say this power SC. Let us call it as power SC. So this power SC is equal to what? It is the power due to the current flowing in IC. So it comes out to be, so here let us, you see the IC, the current which is flowing. What is the voltage which it is seeing? It is seeing the voltage, you see VCA. Okay. So the voltage it is seeing is VCA. So let me first draw the phasor diagram, then you will understand what I'm talking. Okay. So this is IA. This is IB. This is IC. Okay. Now in these two windings, we want to write down the power consumed in these two windings. Okay. So what is the power in these two windings? I'm trying to write down. So you see the current IB, okay, is flowing in the winding where VAB winding, right? So VAB winding and current IB decides the power. So voltage across this is VAB and current through this winding is IB. Okay. So let me first draw here. So if I draw this, this is IB. Now you will see that this VBA will come out to be here, like VB, and then you, if you take minus VA, and then you draw this vector diagram, it will come out to be VBA here. And if I draw the diagram here, so you will see that VCA will come out to be here. Okay, VCA. So this, so you see this total angle VBA with this, so it is like this, that this is phi. This IB is making with this VBN phi angle, which is the, what you say, power factor angle. So here also VCN is making phi. This is 30. Okay. In the similar way, this is 30. Okay, this we know, right? We know, we have seen it in the last class, that how the line to line voltages are leading their respective phase voltages by 30 degree. Okay, like that. Now you see here, so let me write down this thing. So you will see that this SC, which is the power in this winding. Okay, the power in this winding is SC and power in this winding is SB. So SC you will see will come out to be VI 30 plus 5, and here SB will come out to be VI minus of 30 minus 5. Okay, and if you simplify these powers, like you expand these expressions, so this total power SC plus SB will come out to be root 3 VI at an angle phi. Okay, so I'm not what you say expanding on this because it will consume some time, but if you calculate it, it will come out to be root 3 VI phi. Okay. So this is how the power for this open delta winding is there. Actually, open delta is not what you say, not, there is no question today in this assignment, but I have discussed it so that in case some theoretical question or something is asked, maybe something is asked like how much power reduction is there, or if suppose your suppose some question would be like, if suppose your load is taking this much of power, so what is the power of each of these windings consumed, like that. If suppose this kind of question is there, you can answer it. Okay. Now, so you know that if the total power is this much, so the each of the transformer power is 1 by root 3 times the magnitude, right? And their power factor is 30 plus 5 and 30 minus 5, like this. So this information you can at least answer. Okay. Now what is remaining is we are remaining with the parallel connection of the transformers, right? So let us discuss the parallel connection of transformers. So in the open delta connection in this assignment, there are no questions, but someone can ask you that, okay, the total load power means SC plus SB is suppose some value they will give like 1000 kVA and power factor is like suppose 0.8. So they will ask you, okay, what is the power and what are the individual windings power factors? Okay, so that you can answer. Okay, that you can answer using this. Okay, so this is also important. So these two are important. Okay. Now let us come here. So parallel connection of transformers. So I am writing here some conditions. Okay. So conditions for the parallel connection of transformer. Conditions. So for I'm writing some common conditions for both single phase and three phase transformers. Then I will write specific condition for the three phase transformers. Okay. So here, what is the first condition? The first condition is that the polarity should be same. So what do I mean by this? So this is the winding. This is suppose one single phase transformer having polarity dot like this. So the second transformer dots should be connected to the dot only. Okay. So this is what I meant by same polarity. So same polarity. Then what will happen is if we do not do this, then there will be a short circuit. Okay, because you see you will see that for paralleling of the transformers there has to be like equal voltage ratios and equal voltage ratings, right? Because parallel, when you can connect the two voltage source in parallel if they are having same magnitude. Okay, so from the same logic will be having the same magnitude. But if suppose you connect in the reverse way, then what will happen is this plus V and this minus V will create a zero voltage across some load. So it will create a short circuit. Okay. So a huge current will flow. So that is why it is important that the polarity has to be same. Now, this is the must condition. Like it is a very necessary condition. Now, the second condition is, which I said, equal voltage ratios and same voltage ratings. Okay. This is a must condition. Now, what happens that in actual systems, there may be small slight difference in the voltage ratios. Okay. So if that happens, so here, so let me draw it. Here you are having like this. You are having here like this. Okay. So there may be a slight difference in the voltage ratio because in actual systems also there is some slight difference. Okay. Because practically no transformers can have exact same voltage ratio. So there may be like 1 volt or some 2-3 volts difference like that. Okay. That is allowable. Okay. Now what happens if there are two different voltage ratings, then what will happen is that small, you see, the note is that a small difference in voltage ratios are allowable. Okay, small difference. Voltage ratios can be allowed. So you will see in today's assignment also there are some questions where this small voltage ratio difference is there. Okay. Now what happens due to this? Due to this there is a circulating current. Okay. So what will happen? The circulating current will flow between these two windings. Okay. So like this. So here I see, because this is circulating in this transformer only, so this current will be flowing like this. Okay. So this is A is to 1. So they are here also there will be IC by A current. So how is this current flowing? This current is flowing within the transformer. Okay, so this current is flowing like this, then going like this, then coming back here like this. Okay, then as per the turns ratio, this current will also flow like this, and then it will come like this. Okay. So this is how the current flows. So what is the magnitude of that current? So the magnitude of that current is like this, that suppose here you have EA and suppose the small difference here is EB. So let us say that this is EB across this. So this is EB. So circulating current is given like this. Okay. So this is how the circulating current is given. So now there is some, what you say, conditions which are valid for only three-phase transformers. Okay. So the conditions for three-phase transformers only. So what are the some more conditions? It is same phase sequence, because in three-phase the phase sequence also matters. Okay. Same phase sequence, which is a must condition. And the second is that zero phase difference between the corresponding line voltages. So zero phase difference between the corresponding line voltages. Okay, this is a must condition. Now let us see some formulas with which we can directly find out what will be the current shared by, or the load shared by the, what you say, parallel connected transformers. Okay, so load sharing, so load sharing transformers having equal voltage ratios. So this is very important. Okay, equal voltage ratios. Otherwise, this formula which I'm going to discuss will not be valid. Okay. So here, this is the case. This is the system you have. So suppose this is the transformer. Its corresponding impedance is Z1. Okay. Then there is another transformer. Its corresponding impedance is Z2. Okay. And so on till Zn En, and they are connected across a load. So let us say the load current is IL. So what we have to find is what will be the current I1, what will be the current I2 here, what is the current IN. Okay, so you will see, because these transformers are what you say having the same voltage ratios. So this E1 is equal to E2 is equal to E3 is equal to En, which is equal to, suppose, let us say some voltage ratio V1 by A. Okay, like this. Now you see, because so here what will be the, so because you see they are parallel connected, and these E1, E2, so on, En are equal. So what it says, that the remaining this voltage drop I1 Z1, I2 Z2, and so on, In Zn should also be equal for the parallel connected system, because this potential is same. Now in this potential, this part are all equal, so this the voltage drop across these impedances should be same in a parallel connected system. So you will see that this means, this implies that I1 Z1 should be same as I2 Z2 should be same as In Zn. Okay, so you will see that this will give that the current in the jth path. Okay, so you see this has to be equal to IL by parallel combination of this all these impedances. So from this relation, what we get? We get that the current in the jth transformer will be IL by Zj. Remember, in ohms, okay, not in per unit. By sigma 1 by Zk in ohms 1 to n. Okay, so in this way you can find the current shared by the particular transformer out of the total load current. Okay, when they are having equal voltage ratios. Okay, when they are having exact equal voltage ratios. Similarly, power also you can find out. So power will be what? Power will be like this. So power also will be Sj star is equal to SL conjugate by, because the voltage is same, if I multiply voltage here, so V conjugate, if I multiply on both sides, so this will become as power conjugate. So that is how it is coming, because voltages is same, so we can multiply. Okay, so K is equal to 1 to N 1 by Zk ohm. So using this you can directly solve for the question, okay, which is having equal voltage ratios. Now let us go to the questions. So let us see the questions of this week. So our first question is on the Scott connection. So we have discussed the Scott connection theory, so you will understand how to solve this question, okay? So here they are saying that in a Scott connected, if a Scott connected transformer takes power from a 1100 line to line three-phase supply. Okay. So here we are giving V1. You see V1 we have discussed in the Scott connection. Okay. So they are saying that this line to line voltage V1 is 11 kV, 11,000. Okay. And delivers power to two single phase 75-volt furnaces. So this is 75-volt furnace here. This is 75-volt furnace here. Okay. And furnace 1 is consuming 250 kilowatt. Furnace 2 is also consuming 250 kilowatt. Okay. Now, what we have to find out? We have to find out that what is the RMS value of current IA. Okay, so we have to calculate the RMS value of current IA. Now we have seen that what will be IA? IA will be nothing but IF by the turns ratio. So if this turns ratio is like this, 80 is to 1. So IA by IF should be 1 by 80. Okay, and what is 80? 80 we know is root 3 by 2 N1 by N2, and this is also equal to what you say, because see, this is also equal to root 3 by 2 V1 by V2. We have seen this. Okay, so you see here. So this is the case, right? Root 3 AT is root 3 by 2 N1 by N2, which is equal to root 3 by 2 V1 by VT2. VT2 is the voltage here. So this voltage they have given as 75 volts. So that is what I'm directly writing like this. Okay. So N1 and N2 information they have not given, but we can find out AT by using this root 3 by 2 V1 by V2 relation. Okay. So that is what we will find out. And then when we find out IEF, we can get the current IA as IEF by AT. So what is IEF? So for calculating the IEF, we have to use this data. So they are saying that furnace 1 is consuming 250 kilowatt at 0.8 power factor lagging. Okay, so what is this? So this, and you remember, you can treat this as single phase loads. Okay, single phase, so there's, you can treat it as single phase, because as I said that an n phase system is made by n single phase systems, so a two phase system is made by two single phase systems. So you can treat this as single phase, you can treat this as single phase. Okay, so what is the formula for the single phase load? So the formula for single phase power is Vi cos phi as 25 kilowatt. Now here V they have given as 75. I we can find here, which is IEF. Cos theta is 0.8 and this is 250 kilowatt. Now since they're asking only the RMS value, you can directly, what you say, calculate it like this by 75 into 0.8 and then use it here. Okay, and then use the calculated value of IF here. So IA will become 250 kilowatt by 75 into 0.8. Now what is AT? AT is root 3 by 2 N1. N1 or V1, we can write it as V1, 11,000. So let me write it properly. So IA is 250 kilowatt by 75 into 0.8 into root 3 by 2, 11,000. And this is what here we have. N2 is how much? N2 we can write it as V2. So this is 75. Okay. So you can calculate this. You will get the RMS value. Okay. So it's RMS value you can get. But if suppose you also want to calculate the phase angle, so we know that here, because they have mentioned that this current, basically this is a lagging power factor. So here we can write it with a lagging power factor minus cos inverse 0.8. So it is like this, that you have VA here, you have VB here. So this is the IA which is lagging. This is the IB which is lagging. So this is phi. Okay. And we know that this IA and capital IA are in phase. Okay. So whatever is the phase angle of this IEF or small ia, that will be also the phase of this capital IA. So if suppose they ask you the question, okay, what will be the phase angle of capital IA, you can directly write it as that. Okay, so this is how you will calculate for this. Now they're asking you to estimate the current IB, okay, RMS value. So see, first of all, how you can save the time is that, you know, when you have given a balanced load, okay, balanced load means you have given the equal loads to both of these, what you say, furnaces. So what will happen, due to these equal loads, the equal magnitude of current will flow. And when the equal magnitude of current, which is like this, so it is here like this. Okay, so as I drew the phasor diagram, so this is your VA, this is VB, So here you have IA, here you have IB. Now this, because these two loads are same and they are also having the same power factor, same what you say wattage consumption. So this magnitude and the phase angle of both the loads are same. So suppose this is I, this is I. And we know that when both of them are having the same magnitude and same phi, then what will happen is that this is IEF and this is something they have written, right? IGH. Okay. IGH. So this is IEF. This is IGH. And we know that when we give a two-phased balanced loads to these two-phase voltages, then what happens is that the currents which we get are balanced, right? We have seen that also. So we have seen that the magnitude of these currents, IA, IB, IC, they all come out to be the same. Okay. So you will see that this magnitude of IB, IC, and IA comes out to be same. Okay, you can apply this tan 30 and by this you will get the same magnitude. Okay, so you can see that we have the same balanced currents if there is same what you say this is balanced with any power factor but same. Okay, but same power factor. Okay, load leads to a balance three-phase currents. Okay, in primary side. This we have derived here. So even without solving for this, you can directly write that, okay, that the same magnitude you will get here also. But if you want to solve by the phasor method, you can solve it. Okay, but it will save you time. That is why this is important, all this discussion. Okay, so if suppose we are told to find IB, so we can find it out like this: IBC minus IA by 2 phasor addition. Okay, so you can found it out like this also. So here we have IBC minus IA by 2. Okay, so this is what is my IB. Now I in the so here what they have taken is they have taken it a reverse way. They have taken that this phase VB is leading the VA, but you can write it in the other way also. So what will happen is that your IBC current, in the same way you can find out the current magnitude, that VI cos phi is how much? 250 kilowatt. So IGH will be 250 kilowatt by 75 into 0.8, and this angle I am taking it as minus 90 minus cos inverse 0.8. Minus 90, why? Because here I took it as minus cos inverse 0.8. I can either write it as 90 minus cos inverse 0.8. So this will become only minus cos inverse 0.8. But among them, there should be 90-degree phase shift. Okay. So here by using this also, I can find it out. So here I can write IGH. So here this is 250 kilowatt by 75 into 0.8 minus 90 minus cos inverse 0.8. And from the previous question, we have found out what is basically IA by 2. So here, now another thing is that, see, this current IGH is here, but we have to get IBC. Now what is IBC? IBC will be IGH by AM. Okay, and what is AM? Because this is AM is to 1. Okay, and what is AM? AM is nothing but simply 11,000 by 75. Okay, so IBC is IGH by AM. So here IB becomes this multiplied by 1 by AM, right? So 1 by AM means 75 by 11,000. Okay, and minus IA by 2. So IA we have found from the previous question in that way. So that you take by 2. So you take this 32.08 minus 36.86 by 2. Okay. So if you solve for it, you will get your IB. But you know very clear cut that without solving for all this, because they're asking you the magnitude, so you know that because this is a two-phase balanced load means they're having the same what you say wattage and same power factor angle. So because of it, the currents which results in this three phases IA, IB, IC, they comes out to be also balanced. Balanced means they will have the same magnitude and they will be phase displaced by 120 degree. Okay, so even without solving this, you can find out the current IB magnitude as same as this 32.80. If you solve for this, you will get this current. Okay, you will get this magnitude. You can solve for it. Okay, so if you solve for it, you will get that. Now let us go to the next question here. Naturally, because they have taken it in the other way, they have taken it IB is leading IA like this, they have taken the thing. So here what will happen is that this minus 36 point, you will get this current. Okay, you will get this phase angle if you solve for it as per our discussion, as per our derivation in the beginning of the class. So we are not following this convention, we are following this convention. Okay, so you will get this, but the magnitude will come out to be same. Okay, now let us go here. Now again they're actually asking you to estimate the current IC. We know how to estimate the because the current IC will also have the same magnitude, so you don't need to solve it again. But as per this discussion, IC is what? IC is minus IBC minus IA by 2. Okay, so you can solve like this also, but if you have, since you have already solved for the previous question, so you can directly enter the magnitude as the same. Okay, because it is a two-phase balanced load. Is there any doubt till now? Okay, so if you have any doubt in the class, so ask me. Okay, then I'll tell. Now let us go to the next question. Now in the next question, what we have is that we have two single phase transformers which are connected in parallel. So this is like this. So you have two single phase transformers which are connected in parallel. Now you will see that their voltage ratios are what? This is 6600 by 440 and this is 6600 by 420 volts. So you can see that there is a difference in the voltage ratio, and this is their 1 second. And this is their what you say load impedances in per unit. Okay, so this per unit, all whenever this per unit impedance is given, it is given on the transformer's own base. Okay, so you see this per unit impedance is given like this. So this ZL 1.5 plus J 4.25 pu. So pu means this percentage means into 10 power minus 2. Okay, so this value is on its own base, so on transformer 1 base. So transformer 1 base means its power rating is 300 kVA and line to line or phase, because this is single phase, so this phase voltage, okay, is 6600, or in whatever side you are calculating. If suppose you are calculating the voltage on this side, then you will take 66 primary side, you will take the voltage base as 6600. So this is P base, or V base primary is 6600, V base secondary is 440 volt. Then in the same way, this ZL is on the transformer 2 base, where the power base is 400 kVA, voltage base on the primary side is 6600, and voltage base on the secondary side is 420 volt. Okay. Now what we have to find out, because these voltages are unequal, so we have to what estimate? We have to estimate the no load circulating current on the secondary side. So on this side, we are supposed to find the IC, no load circulating current. Okay. So this circulating current we are supposed to find on the secondary side of the transformer. So we have seen this discussion here. So how to get the circulating current? Circulating current is nothing but this EA minus EB divided by the impedances. Now these impedances you have to take in ohms. Okay. So these impedances ZA impedance of the transformer 1 and ZB impedance of the transformer 2, they, you have to take it on their own base. So that is what we will do. So here we have EA as 440 volt. So EA is 440 volt. EB is 420 volt. And what about ZA? So ZA will be 1.5 plus J 4.25, because it is percentage. So divide by 100 into its what you say Z base. So Z base, how you will calculate? You will calculate it as basically voltage base by current base. And what is the voltage base? Voltage base is 6600. And current, what is current base? Current base is nothing but power base by voltage base, because V into I is power. So I have to find current base, means power base is known. So this is how I find. So this becomes V base square by P base. Okay, so this is how we get the Z base. So for transformer 1, so ZA base is V base square. So because we have to find the no load circulating current on the secondary side, so we will be taking the V base on the secondary side. Okay, so secondary side is 440 volt. So this is what we will take. We will take 440 square by power base is 300 kVA. So this is 300 kVA. So this is what we have to multiply. So this is in per unit. So if we multiply by this Z base, ZA base, then you will get ZA in ohms. Okay. Similarly, ZB is what? ZB is 1.75 plus J4 in percentage into ZB base. Now what? So this you will give me ZB in ohms. Now what is this ZB base? So ZB base on the secondary side is what? So it is V base square by P base. So V base square of the second transformer is on the secondary side is 420 square. So this is 420 square divided by P base, which is 400 kVA. So this is 400 kVA. So this is ZB base. Okay. So like this, you will get ZA ohm and ZB ohms. So if you calculate, you will get this as ZA ohms and this as ZB ohms. Okay. Now, as per the circulating current formula, this is what? This is EA minus EB by ZA ohm plus ZB ohm. So if you do that, you can get the current. Okay. So this is how you can find for the current. Now they are asking, whenever they're asking in this way in ampere, so they're asking you the RMS value. Okay. So in the answer, if it is numerical type question, you have to enter the RMS value. Okay. Is there any doubt in this question? Okay. So let us move to the next question. Now this is the continuation of the same data. So in this question, what we have to do? We have to calculate the ohmic losses caused by the no load circulating current. So as we know, ohmic losses are what? Ohmic losses are nothing but your copper loss. So copper loss are what? I square R loss. Okay. So here we know that circulating current I square, IC square. So this will be your IC square. And what is the R equivalent? So R equivalent here is RA plus RB. This will be the loss, because circulating current, how the circulating current is flowing? Circulating current is flowing like this. circulating current is flowing like this. So it is experiencing in the series part both the RA and RB. Okay, so it is experiencing RA and RB in the path. So here there will be IC square RB losses, and here there will be IC square RA losses. So here if we add the two losses, then we can get the total loss. Okay, so see, this is in watts. Okay, if they would have asked some other loss, like suppose what is the reactive power loss, like that. So, okay, so that would have so in that case what you would have taken, you would have taken I square X equivalent. Okay, where X equivalent would have been XA plus XB. So this is RA plus RB. So from the previous question, we have the magnitude of circulating current. So that is why, see, you will get worried that this is so much of calculation, but this only one calculation of one question is equivalent to the calculation in three questions. Okay, so this way it will save you time later. So don't worry. Okay, and do it very carefully so that there are no silly mistakes. Because if there is mistake in one question, then what will happen in continuation, there will be mistakes in other subsequent questions also. Okay, so give time in the first question, do not hurry, do not make silly mistakes. Okay, apply the formulas properly. So here you have this IC current. So this IC is 414 square, and from the previous calculation, by converting it into ZA ohm, ZB ohm, we have the resistance part of that ZA ohm as 0.00968. So this is 0.00968 plus this is what, this RA part of the ZB is 0.0077. So this is 0.0077. So if you solve for it, you will get the ohmic losses. Okay. Now we move to the next question. Now here what we have to determine, we have to determine the no load LV side terminal voltage. So what does this mean? So this is how your transformers are connected. Now here this is EA. Okay, this is, so let me draw the secondary side very carefully. Okay, this is like this. So you have EA, because we have to find LV side or secondary side terminal voltage. Okay, so this is ZA. Then we have the circulating current paralleling cable in which the circulating current is there. Okay, now this is EB, this is ZB, this is the current here. Now current is flowing like this. This is IC, then IC is going here, then IC is going here, then IC is coming out here, then IC is going here. Okay, so they're asking you to find what? They're asking you to find this voltage. Okay, VA. This is also VA because this is parallel. So there are two ways to solve for it. VA can be EA in the direction of current. If we apply KCL, then there will be voltage drop across ZA. So it will be minus IC into ZA. Or VA can be EB, and in this opposite direction, in the direction of current there is voltage drop, but we are moving in the opposite direction towards VA. So this is EB plus IC ZB. Okay, so you can solve it in either way, you will get the same answer. Now EA is what? EA is 440 volt. So this can be 440 volt minus IC into ZA, or this can be your 420 volt plus IC into ZB. So here they have solved using this information. You will see that from both the calculations, it will come out to be same. Okay, so if you solve for it, you will get the answer, this one, this answer. Okay, so is there any doubt here? This is very simple questions. Okay, This one is this is a simple question. Okay, so you can try and see whether you are getting same answer using both the ways or not. You will see it will come out to be the same. Now let us go to the next question. Now here again we are given the data for the 4 questions. Okay, so here what we have this 175 kVA. Its per unit resistance of this transformer is 0.015. Per unit leakage reactance is 0.07. Now see, there also another way of writing it as 15% and 7%. So this can be written either as in 15%, 7% like that. So it was written previously like that in percentage, or it can be written in that directly like this 0.015, 0.07. Okay, and this is the no load secondary voltage. Then here we have 5 to 5 kVA, 0.02 pu, 0.065 pu leakage reactance. This is 420 volt. So you can see that there is a mismatch in the voltage. Now they are saying that together they have to share a 700 kVA, 440 volt, 440 load with power factor this much. Now they're asking you to estimate the secondary side circulating current at no load. So this we know very well, right? So this is in per unit. So we have to first what you say as per the solving for circulating current. So for solving for circulating current, it is like this. If EA is greater than EB, so it is EA minus EB by ZA in ohms plus ZB in ohms. If EB is greater than EA, then you have to write it as EB minus EA by ZA in ohms plus ZB in ohms. Okay, so this is the circulating current. So this we have solved in the previous question also. So here just you have to do is you have to calculate ZA ohm very carefully. So here ZA ohm will be this 0.015 plus J 0.07 into ZA base. So ZA base on the secondary side is this voltage square V square by P base. So V square, so this is V base square by P base. So V base square is 440 square by power base is 175 kVA. Okay, 175 kVA. Then ZB ohm is what you say how much? It is 0.02 plus J 0.065 into ZB base, and you can calculate the ZB base in the similar way. Okay, so this is how you can calculate for the circulating current. So in the like how we have done in the previous case, like this we can solve for the circulating current here also. Now let us go to the next question. Now in the next question, what we have to find, we have to estimate the current supplied by the transformer when the load is shared by the two transformers. Now remember this thing, this formula which I wrote. Okay, this formula which I wrote, this is only valid when the transformers have equal voltage ratios. Okay, but you will see that here the voltage ratios of the transformers are not equal. The voltage ratio here is like here on the secondary side you have 440 volt, and here on the secondary side you have 420 volt. So they are not the same. So what to do in this case? So this is how you will solve here. So here what they have done is, so this is the paralleling like this, right? So this is 440 volt on the secondary side. I'm drawing the secondary side circuit. Okay, so it can be drawn like this. 1 minute. So this is Z1. This is 440 volt. This is Z2. This is 420 volt. So this is I1. This is I2. This is I2. Okay. And then on here we have a load. The load is having I1 plus I2. Okay. So how you can do this? So this, you see, they together they have to share a 700 kVA ampere kVA 440 volt load, okay, with power factor 0.8 power factor lagging. So first of all, we can calculate what is IL. So IL from this data we can calculate. So this is what VI cos phi. So this will come out to be 700 kVA by voltage into cos phi, and this is lagging, so here we can write it like this. So this is our I load, okay. So this is one equation. Now what so here how we can solve for it. So we can solve for it. So for solving it, we have two unknowns, which is I1 and I2. Okay, Z1 Z2 we know. Z1 Z2 we have calculated in Z1 ohm and Z2 ohm in the because it is the same data. So here we have calculated it like this. Okay, so this we already know. So what are the unknowns? So there are two unknowns, I1 and I2. So there are two unknowns, so we need two equations. So what will be those two equations? So here the one equation is simply this, what you say, I1 plus I2 is this value, I load, and the other equation is you can write any of the KVL equation. Okay, so any of the KVL equation means 440. Okay, okay. The thing is actually here, if you will see, so you see this 440 volt, if we take it at angle 0, this is the tricky part. So if we take this 440 volt at angle 0 across this load, then what will happen? This will come out to be 440 angle theta, 420 angle theta. Okay. So theta 1, theta 2, like this. So this is the tricky part. Okay. Because the voltages which they have given, they have only given the magnitudes. Okay. So how you can solve for it is, so here, so this is how you can solve for it. This is another way of solving it. It's the same thing, but they have written it like this. So here they are writing one KVL loop here. They're using the KVLs, not the KCLs, because in that way we are assuming that, okay, we are not assuming this as 440 angle 0. Okay. We are not assuming this at 440 angle 0. We are assuming that, okay, there can be something else also, but it is not 440 angle 0 exactly. Okay. So that it will give us some flexibility. So here you see, we can write the KVL here in two loops. So we have the KVL equation here. So here you see this E1 minus of I1 Z1, and through this Z we have I1 plus I2. So this will be E1 minus I1 Z1, minus of I1 Z1, and then minus of I1 plus I2 into Z. Okay, like this. Then similarly we can write for E2. Then here they are using these two equations, and they are saying, okay, we will only find the magnitude. We do not care what is the E1 theta or E2 theta. Okay, we do not care. We are just considered about the magnitude. So if they take the magnitude in this way, we can get the value. That magnitude will same. Okay, that is why they have solved it in this way, and they're solving it in the magnitude way. Okay, so you can find just the magnitude use like that. So this is a little bit of a lengthier question. So that is why this question also have like three parts. Okay, so you can spend some time in this question. So here they're asking you to solve for I1. In the next part they're asking you to solve for I2. So naturally when you solve for this first these two equations, so you will get both I1 and I2. So in this way your two questions will be solved simultaneously. Okay, so I understand that this is a bit of a lengthier, what you say, it is a lengthier calculation, but it is helping you to solve three questions simultaneously. Okay, so in this way you can write the KVLs, or maybe you can also use the KCL equation also. Okay, you can use this one KCL, and maybe you can use only one KVL. But see, they have already utilized the KCL here only. You see, so they have actually used all three equations. Okay, so they are writing one KVL loop here. They are writing one KVL loop here, and while taking the current through Z, they have taken it as I1 plus I2. Okay, so they have used so you have to solve it in this way only. Okay, you have to write the KVL loops only. So if you write the KVL loops, you can solve for I1 and I2. Okay. So now let us go. There is no direct way of solving for this, like how it was directly here as per this formula. If it is equal voltage ratios, it is not direct. You have to apply KVL, okay, proper KVL. It is lengthy, but it is they will give you at least 2 to 3 questions in the same, what you say, so it will be utilized somewhere. Like they may ask, okay, you have found the I1, so what is the ohmic losses in transformer 1, what is the ohmic losses in transformer 2? So when you find I1 magnitude, you can calculate the ohmic losses as I1 square R1. You can calculate ohmic losses as I2 square R2. They can calculate total ohmic losses in the load, so you can calculate I1 plus I2 whole, well, matlab, whole square into this impedance are like that. Okay, so in this way they can ask many things in the same question. So don't worry that if you're solving this much, okay, they will ask at least 2 to 3 questions in the same data. Now here you see, here so for this what they're asking is that we on the basis of the I1 and I2 which you have calculated, you have to see whether which any of the transformers have exceeded their ratings or not. Okay, so you can calculate the transformer current rating. So this current rating you can directly find. So this I1 rating is 175 kVA by 440, and I2 rating is 525 kVA by 420. Okay, so in this way you can calculate I1 rating, I2 rating. Okay, and once you have calculated this rating, you can compare the I1 and I2 value. So I1 value from this came out to be 496 and I2 is 1004. So I1 is 496 in this connection and I2 is 1004. So you will see that the I1 rating is 397, I2 rating is 1250. So I1 current is more than its I1 rating and I2 current is less than its I2 rating. Okay. So you will see that which transformer has crossed its ratings. So the correct answer is transformer 1. Okay. So that is it. This was the last question of this assignment. So is there any doubts? So if we do not have any doubts, so we will conclude the class here and I'll upload this video also and the slides also. Okay. So is there any doubt in this assignment, this solutions? Okay. Okay. So I understand that so someone is asking something. Okay, 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 okay. So I understand that this last question solution is a little bit lengthy, okay, but you will see that they will at least ask you minimum 3 questions. Okay, they can also ask 4 also. So if it is taking some time to solve for this, don't worry, it will be at least 3 to 4 numerical questions will be asked on the same data. Okay, so don't worry about that. Just do not do any mistakes, that is all. So these things are all there. If you have any doubts, you can ask me in the next class also. You can try to see the notes whatever I've discussed and maybe try to what you say, use them in this week's assignment questions. And if you have any doubts, you ask. Okay, so that is it. If we do not have any more doubts, then we will stop the class here. Okay, so so that is it. Okay, okay, thank you. So you can leave if you have no doubt. Okay, okay, thank you. ठीक है, then I'm stopping the class here. Okay, okay, so you can leave. Okay, okay then.